Hello, my name is Femi, and you're welcome to Easy Epidemiology. This is the outline of the presentation. Epidemiology is a branch of medicine which deals with the incidence, distribution, and possible control of disease. The incidence of a disease is the number of new cases in a specified time, while prevalence is the total number of cases in a specified time, that is, new and old cases. A mnemonic to remember prevalence: as all cases, we have AL representing all, and the N here in incidence is new cases. So incidence, new cases in a population in a specified time, prevalence, new plus old. To the right, we have the epidemiologist's bathtub, where the prevalence forms the pool in the bathtub. The incidence as well as the recurrence, they add to the pool, while recovery from disease and death from the disease removes from the pool. Here is an example of information provided about Plague. In 2017, we have 5,000 new cases in a population of 900,000, where we have an existing 145,000 people who has diabetes mellitus. Now, from the question, we have incidence of diabetes type 2 in 2018 per 100,000. So in 2018, we have 10,000 new cases, 150,000 existing cases in a population of 1 million people. So we have 10,000 per 1 million, but the question is asking for incidence per 100,000. So all we do is divide by 10. So we have 1,000 per 100,000. The prevalence of type 2 diabetes at the end of 2018 in percentage. That one, we'll calculate it by adding 150,000, which is the existing case, plus this 10,000, which is the new case. Remember, we said prevalence is what? Number of new cases and the old cases. And this will give us 160,000 per 1 million population. Now, if 1 million is 100%, what is 160,000? And that way you cross multiply and you get 16%, which forms the prevalence in percentage. We'll move to descriptive measure, which is our mean, median, mode, and range. The mean of a statistical data is the sum of all values in the data divided by total numbers of values. So when we look at this example here, 4243610, we sum all of them together and divide by 1, 2, 3, 4, 5, 6, 7, divide by 7. This will give us the mean. The median is the middle value when the data are arranged in order. So 4243610, we rearrange it to get this, and this is our middle number. This is the median. The mode is the most frequent number, which is 4 in this case. We have 4 in 2 places. Range is the difference between the highest and the lowest value. P-value is used to determine if an outcome is statistically significant, and the number we need to remember is the 0.05, not 0.5, 0.05. Very important. When your p-value is less than 0.05, it is statistically relevant. And if it is greater than 0.05, then the result is lucky guessing. Epidemiological study helps to link our idea to data and prove an association between exposure and disease. The first epidemiological study is the British study of 1956 that linked smoking cigarette with increased risk of lungs cancer. Types of epidemiological studies, we have the non-experimental and the experimental. Under the non-experimental, we have population-based and individual-based. But all these, it's not relevant for PLAB. Though it's good as an epidemiologist to know all this, but for PLAB, we'll focus on a subset of this total information. So this is what we're going to focus on in this presentation. Epidemiological study is broadly divided into observational studies and experimental studies. Under experimental studies, we have randomized control. And under observational studies, we have your case control, cohort study, and cross-sectional. What is the difference between observational and experimental control? And the answer lies in randomization. Now, when you have 10 people in a study, say 5 females and 5 male. In experimental study, you want the way of selecting participants is more random, where let's say in one case you want 3 males and 2 females, while in the other you want 3 females and 2 males. You randomly pick the people that's in your group and you separate them into interventional group and control group. We'll talk more about this. Observational studies is selected, that's the participants are selected based on some intrinsic properties, like let's say a male or a female. We begin with case control studies. One thing I would like us to remember about case control is case and control. Hello, doctor, you have a case. What does that mean? That means you have a patient who has a disease. So apply that thinking to case control. In case control, you begin with the case. That is, you begin with the disease. Once you appreciate this, you have solved everything about epidemiological studies. Case control is a study that begins with the disease. You have your case group and you have a control group. You compare them. Then you look back in time. That is the classical case control. You look back in time. That's retrospective, to collect data and establish causality. So as we say, the case control begins with the disease. You have your case group, you have your control group, you look into time to establish causality. We have our timeline, so we start with the disease. For example, let's pick patients who has mesothelioma. You have a group A, these people have the disease, and you have the control group that does not have the disease. Now you go back into time. Now don't mind the arrow. This arrow is pointing towards exposure. This is just connoting that you are moving from disease to exposure. But actually, you're moving back in time to collect data. Maybe company records, the history you collect from people, you understand, to establish exposure. In this case, let's talk about asbestosis. That okay, the people who had mesothelioma had some exposure to asbestos. 4 out of 5 worked in a factory where they were exposed to heavy asbestos. Now in the control group, only 1 was exposed, and even this very one did not come down with mesothelioma. And with this, you can make your inference. The advantage, one of the major advantage of case control is that it is comparatively cheaper. That's when we compare to cohort studies. We'll discuss that in a minute. Then one can analyze various exposures, because you're starting with with the disease already. So you can play with a lot of exposure that's as a causal agent or as causal factors to the disease, but you only have one disease. Now, only a small sample size is required as the study is starting with cases. The disadvantage is, or one of the disadvantages include what? Recall bias. As you're taking history, some may lie blatantly, others might have forgotten something and they will decide to confabulate and just give you a story. So since you are depending on people's memory, you are depending on data from the past that might have been altered. So we have recall bias. Then you can deal with one disease at a time. Since you are starting with disease, if it's mesothelioma, you are dealing with only mesothelioma. You don't have the luxury of dealing with another disease. Now, in cohort study, the information here is almost the exact opposite of case control. Case control, you are starting with case and you are going back in time to look for what? Exposure. In cohort studies, you are starting with exposure. You have your exposed group, you have your control group, then you follow them into the future. Classically, you follow them into the future, you collect data as you go on to establish a causality. So let's say, for example, you have people that are exposed to asbestos. Then you have other people, that's another group, that are not exposed to asbestos. Then you go forward in time, monitoring them, who will develop disease, who will not develop mesothelioma. Then you now found out that after 10, 15, or 20 years in your studies, 3 out of 5 people with asbestos exposure, they develop mesothelioma. Whereas only 1 without asbestos exposure developed a mesothelioma. So you can infer that, okay, asbestos is a risk factor to mesothelioma. The advantage of cohort studies is you can pinpoint the causal agent and you can study multiple diseases at the same time. You have only one exposure that you are starting with, so you can see if smoking can cause more. Let's say, for example, the exposure you are looking at is smoking. Okay, you can ask the question: can smoking cause multiple pregnancy? Can it cause pneumonia? Can it cause cancer? Can it cause COPD? You have the luxury of all that. The disadvantage here is that the study takes a long time and it consumes a lot of resources. Participants may die or they may get tired and run away, and this will alter the result. Randomized controlled trial studies, it's the goal of randomized controlled trial is to provide intervention. So you have your 2 groups. Group A that are randomly selected, and group B also randomly selected, although they have similar characteristics. You provide intervention to A and there is no intervention in B. You follow them over time, you compare their response, and you can draw your inference. The features of randomized controlled trial, as we said earlier, randomization. Then there's another important concept, blinding, which is concealment of group allocation from one another that are involved in the clinical research studies, and this is to prevent bias. Randomized control study, the intention of randomized control study is to treat, and there's an ethical angle here. You don't induce, and when you are providing intervention to a population, you should be sure that this intervention is not dangerous, it will not harm them. That's the ethical viewpoint. Then the study is prospective. You provide the intervention, you study the response of the participants in both groups, then you compare and conclude. Now, this is a summary. When you're beginning your study with exposure, smokers, non-smokers, immediately you're thinking cohort study. And classically in cohort studies, you have your exposure, you follow them forward in time. That means it's what? Prospective. Then you compare your outcome. You are not going to the smokers and offering cigarettes to one group. When you start to intervene or you provide something in a study, it changes from cohort and becomes randomized case trial. Now, when you begin your study with a disease, that's case. Always remember, once you see a case, which is a disease, once you see disease beginning, that's you're starting a study design with a case, that is case control. Then you go back in time to find out the cause of that disease. So classically, case control is retrospective and observational. When you have two randomly selected groups and you offer a treatment, you offer treatment to one group, offer placebo or no treatment to the other group. In this case, blinding is very important. You follow them over time. That is prospective. It is interventional. This is what? Randomized control trial. A cross-sectional study is an observational study, and it takes a snapshot of a community at a particular time. It helps to measure the prevalence of disease in a population. Now, one important thing about cross-sectional study is you are checking the exposure and you are checking the disease at the same time. Now, look at this is an example. For instance, you want to know the number of people who are depressed in a community. Then, one of the factors that may lead to depression, let's say living alone. So, I want to know the number of people who are depressed in a community. Then, out of these people, I want to know how many of them are living alone. Or, let's say you want to know the number of people who has coronary artery disease in Jos, for example. And from this, you issue questionnaire. You want to know how many of them exercise regularly. Then you can, at the end of the day, you can say, okay, lack of exercise is an important causal factor for coronary artery disease. As I said earlier, cross-sectional study measures the prevalence of disease in a population, and you are looking for the risk, both the risk and the disease. You are taking care of that at the same time, which is now. Now we'll go to absolute risk. When, let's say for instance, you have done a randomized control trial study, and at the end of your study, you found that, okay, for the control group, 7 out of 10 people who did not receive medication, they developed a disease. Now, that 7 out of 10 forms the absolute risk in that group. That's the number of people who came down with disease divided by the total of number of people in that group. That is absolute risk. Now, looking at the other group that received an intervention, let's say 3 out of 10 had the disease. So that 3 number of people who came down with disease divided by the total number of people in the group, that gives us the absolute risk in that group. It does not compare groups. You are not saying, hey, how is this one affected by the other one? No. is just absolute risk of one group, absolute risk of another group. That's the risk of coming down with a disease. Now, how do we represent this information on a 2x2 table? Because this is very important. On a vertical column, we have exposure and no exposure. While on the top row, the horizontal row, you have disease and no disease. This is our 2x2 table. This total is just an addendum. It's not particularly important, but we will use it here in this example. But what is critical here is exposure, no exposure, disease, no disease. Now we say 3 out of 10 in the exposure group developed what? A disease. So these ones are exposure, exposed to medication, exposed to an intervention. 3 here out of a total of 10 people had diseases. Now, the no exposure group, that's the ones that received placebo or did not gain anything from the study at all. He said 7 out of 10. And 3 out of 10 is what? The absolute risk for the exposure group. Whereas 7, that's those that came with disease, divided by total, forms the absolute risk in the no-intervention group. Now, there is a concept of absolute risk reduction. Absolute risk reduction is the absolute risk in the control. The control in this sense is those that did not receive any intervention or those that received placebo, minus the number, that's the absolute risk in the treatment group. And when you sort it, that's 7 over 10 minus 3 over 10. You have 4 over 10. Relative risk, unlike absolute risk, that is just absolute risk of exposed, absolute risk of no exposed. Relative risk from the word go compares the two groups, and this is represented as the absolute risk in the treatment group divided by the absolute risk in the control group. So that's 3 over 10 divided by 7 over 10. That's if we're checking the relative risk of this table. Absolute risk in the treatment group divided by absolute risk in the control group. Now, relative risk reduction is 1 minus relative risk. When you look at this slide carefully, you know that this relative risk is what? ART divided by ARC. That's absolute risk of treatment divided by absolute risk of control. Now, when you take the LCM of this, ARC comes down. Okay, I think you can sort this out instead of trying to explain it. But at the end of the day, you will have this, and ARC minus ART is absolute risk reduction. Therefore, we have relative risk reduction is the same thing as 1 minus relative risk, which is the same thing as absolute risk reduction divided by absolute risk of the control group. Next is true positive, true negative, false positive, and false negative. We will use the information on this slide to explain this concept. Now, 10,000 women were involved in a study looking at a new screening test to detect cervical cancer. So the total number of women involved in this screening, 10,000. 1,000 of the women who had the new cervical screening test had positive results. So the test positive is 1,000. 100 out of these 1,000 who tested positive had colposcopy and biopsy that showed negative result for cervical cancer. So that means 100 is false positive because the screening test showed they were positive, but a confirmatory test went ahead to say they are negative. So 100 out of 1000 false positive. Then the remaining 900, that's 1000 minus 100, they are the true positives. Now, 10 out of the 10,000 of the 9,000 women who tested negative for the new cervical screening test had a colposcopy and biopsy that showed positive results for cervical cancer. So 9,000 women had negative results. The false negatives, that's 10. These 10 from the screening test were negative. However, they had a colposcopy result that showed they were positive. So 10,000, 9,990 false, and that's true negative. True negative. Now to construct our information on a 2 by 2 table, on your vertical line, on your vertical column, you have your test positive and test negative. On your top horizontal row, you have your what? Disease and no disease. So we'll start to insert. Test positive has the disease, so this is true positive. Test positive, no disease, so that's what? False positive. Test negative but has disease, so this is false negative. Test negative and no disease, so this is true negative. And when you can, this is the original question, this is the table representation. This is the original question and this is the table representation. We should be able to do this very fast in the exam because this table is helpful for a number of questions. You can use it to calculate your sensitivity, your specificity, your positive predictive value, negative predictive value, and accuracy. A new screening test called Z1 is used to identify patients at risk of melanoma. 1,000 patients took part in this study, so our total is 1,000. Out of the 1,000 patients, 900 tested positive. So our true positive is what? 9. Sorry, our test positive, not true positive. Our test positive is what? 900. Of the 900 patients with the Z1, 600 of them were later diagnosed with melanoma, and 300 of them had benign skin condition. So our true positive is 600 and 300 is what? False positive. Half of the remaining 100 patients who tested negative to Z1 were diagnosed with melanoma, which is the correct term for this 100. So that means they are what? They are the test negative. They are the test negative. Then 50 are what? True negative. The other 50 false negative. Understanding true, true, false. In another video, I went in depth to explain true, true, false, but here I will simply apply it. Now, sensitivity is a test of positivity and is how reliable a test is to show disease in a sick person. Whereas specificity is a test of fitness, it's a test of negativity, in the sense that how reliable is a test to show no disease, to give you a negative result for someone who is not sick, to give no disease for those who are fit. So in true, true, false, in sensitivity, you have your true, true, false. So as it is a test of positivity, we have true positive, you flip your false, which is false. Instead of positive now, you have false negative. Now, Compare this or contrast this with the positive predictive value. It is still true, true, false. True positive, false positive. We are not flipping. That's the difference between positive predictive value and sensitivity. Now, let's look at specificity. It's still true, true, false. But specificity is a test of negativity. True negative, divide by true negative, and false, you flip. False positive. It is not false negative. Now, contrast it with the negative predictive value. It's still true, true, false, but you are not flipping this. So for sensitivity and specificity, you are flipping, and you have no flipping in the predictive values. Accuracy is more or less of what the test got right, divide by everything. Now, the screening test and the disease, true positive. So the test got this right. These are the numbers that the test got right. The negative test, this is true negative. This is what it's getting right. So the addition of A and the addition of this D, divide by the total cells. That's the value here, the value here. That will give you your accuracy. You can watch the video on easy specificity. I might have, I think I described this concept better there. Sensitivity is a measure of a test ability to correctly detect people with the disease. It's a test of what? Positivity. The test wants to give you positive for sick people. What does it mean if you are giving an example of a test with sensitivity of 95%? And this means that this test will correctly identify 95% of patients who have the disease, but it will miss out 5%. The 5% it misses is what we call the false negative, since they have a negative result but actually have the disease. Specificity is a measure of a test ability to correctly identify people without the disease. So when somebody doesn't have the disease, then that means the test will be negative for the disease. And that's why we say specificity is a test of negativity. It's giving you negative for somebody who does not have the disease. And it's a test of fitness, FI for fitness. Now, what does it mean when you're giving an example that the specificity of our test is 60%? This means that the test will correctly identify 60% of patients who do not have the disease, but will misidentify 40% of them. The 40% will be identified as having the disease, but actually do not. This is what we call the false positive. And there is an inverse relationship between, because look at specificity is true negative, divide by true negative, false positive. There is an inverse relationship between the false positive and specificity. So when the specificity is high, that means the false positive is low. And when the false positive is high, that means the specificity is low. A new screening test, you can pause this, you can read it and attempt it. This is the answer. Pause this slide and take your screenshot. Is what we have been discussing: sensitivity, specificity, positive predictive value, negative predictive value, accuracy, and odds ratio. Epidemiological measures. We have an index case. The index case is the first person that indicates the existence of an outbreak. So let's say there is a jump from an animal to human. There is a disease jump from animal to human. The first person that indicates the existence of this disease, that's the index case. The primary case is the person who first brings the disease into a group. Let's say the primary case will be the person, in the case of COVID-19, the person that traveled from China to Nigeria for the first time. then every other person becomes secondary. As they contract the disease from somebody who knows somebody that knows somebody that knows the primary case. The primary case got it from the index. Primary attack rate is similar to attack rate and is the number of affected persons divided by the total population times 100. Secondary attack rate, number of exposed persons who develop the disease within the incubation period following the exposure to primary case, and is the number of exposed persons who develop disease within incubation period divided by total number of exposed contacts times 100. Thank you for listening. I think after this video, after listening to the video, this will be the best time to jump into Plabable and answer some questions. Thank you very much, and this is the end of Easy Epidemiology. Cheers.